Dear students, now we are going to discuss a problem in mass transfer, particularly in a diffusion mass transfer. In diffusion mass transfer, the problem more specifically related to concentration, velocities, and fluxes problems. So, in a diffusion mass transfer, uh, the masses diffuse from higher concentration gradient to lower concentration gradients and mix. And finally, we are going to find out what about the concentration, what about the mass densities, molar densities. These things we are going to find. Now we move to the problem. So the vessel contains a binary mixture of O2 and N2 having a partial pressure in the ratio of 0.21 and 0.79 at 25 degrees Celsius. So this is a container. So in a container, the blue color dot represents the oxygen that having a partial pressure of 0.29, and then green color represent the nitrogen which having a partial pressure of 0.79 bar, and the container total pressure is 1 bar, which is equal to 10 per 5 Newton per meter square, and the temperature is 25 degrees Celsius, which is equal to 98 Kelvin. Now we are going to find for 5 times. First one is nothing but that is called as a molar concentrations. So first we are going to find the molar concentration, so which can be represented by a symbol that is called as a C. We are going to find C of O2 and C of N2. That is the term we are going to find the molar concentration. So where we are going to find the molar concentration with the ideal gas equation. So we already know some gas equation that is equal to PV is equal to, that is the MRT, or represent that gas constant. Otherwise, in some cases, PV is equal to, that is RT. Some another relation is there. Here we are going to solve the molar concentration, the relation, that is a P of I, that is a partial pressure of this particular component, which is equal to concentration of that particular component to universal gas constant into, that is a temperature. In universal gas constant, it can represent by, that is a R bar. In some book it can be represented as, that is R. So P of I is equal to C of I, that is RT. So these two forms are used in some cases. Then universal gas constant, that is a universal gas constant. In some cases, it can be represented as, there is R bar and R. So which value that is equal to, there is a 8.314 into 10 to the power of 3 joule per kilomole Kelvin. So this is the universal gas constant value. So from using this equation, you are going to find the molar concentration. So P of O2 is equal to C of O2 into R into, that is a T. We are going to find, that is a C of O2, so which is equal to, that is a P of O2 divided by, that is a universal gas constant to temperature. So P of O2, that is equal to 0.21 into 10 to the power of 5. Better we substitute in the Newton per meter square. Universal gas constant, that is equal to 8.314 into 10 to the power of 3. And here the temperature that you can be substituted in terms of Kelvin, so which is into 298. So finally we are going to find, that is a C of O2, which is equal to 0.0085 kilomole per meter cube. Okay. Then again you are going to find the C of N2. Then C of N2 is equal to, that is a P of N2 divided by universal gas constant. Sorry, just wait. P of O2 divided by, there is a R into T, so which is equal to 0.79 into 10 to the power of 5 divided by 8.314 into 10 to the power of 3 into, that is a 298. Finally, we are going to find that C of N2 is equal to 0.032 kilomole per meter cube. Okay. Then after that, finding a molar concentration, you are going to find the mass densities. Second term is, that is a mass density. Then how we can find the mass density from the molar concentration. So here the general formula is rho of I, density of mass which is equal to molecular weight of that particular species into that is the concentration of this particular species. So rho of O2 is equal to molecular weight of O2 into that is a C of O2. So you know that is a molecular weight of O2 which is equal to that is a 32 into C of O2 already you find which is equal to 0.0085. Finally, you are getting that is a rho of O2 which is equal to 0.272 kilogram per meter cube. Similarly, for rho of N2 which is equal to molecular weight of N2 into concentration of N2, molecular weight of nitrogen is equal to 28 into concentration which is equal to 0.032. From that, you are getting the value that is a rho of N2 is equal to 0.896 kilogram per meter cube. You are finding both the densities of oxygen and nitrogen. Then third parameter you are going to find third parameter is equal to mass fractions. Third one is equal to there is a mass fraction. So mass fraction, the general formula is equal to we can represent with small m. So molecular weight can be represented by capital M. So mass fraction of individual components is equal to density of the individual component divided by total density of mixture. Okay, so we find the total density of mixture, that is the density of total is equal to that is the density of O2 plus that is the density of N2. From that you are getting density of total density which is equal to 1.168 kilogram per meter cube. For that is for the value you have m of O2 is equal to rho of O2 you know that is 0.272 divided by 1.168. So we are getting mass fraction of oxygen which is equal to 0.233. Similarly, for mass fraction of N2, we are getting that is a rho of N2 divided by rho of total. So rho of N2 that is equal to 0.896 divided by rho of total which is equal to 1.168. From that, we are getting mass fraction of N2 which is equal to 0.767. Okay, so for oxygen it is 0.233. That is in terms of nitrogen mass fraction nitrogen you are getting some 0.7. The next one, next you are going to find um, fourth one. Fourth one is equal to molar fraction of each species. Next one is molar fraction. Then how we can find the molar fraction? So molar fraction that can be defined by notation that is called as a Yi. Yi is equal to there is a partial pressure of individual component divided by total pressure or total pressure. So you can find then Y of O2 is equal to P of O2 divided by P of total. So P of O2 you are know there is a 0.21 divided by that is a total pressure that is equal to that is 1. So we are getting Y of O2 is equal to 0.21. So that is the molar fraction. Similarly for Y of N2 is equal to P of N2 divided by P of total. So this is equal to 0.79 divided by 1. So Y of N2 is equal to 0.79. Then finally we are going to find average molecular weight of the mixture. Then find the average molecular weight of the mixture. So fifth one, that is the fourth one. Then fifth one, average molecular weight that can define average weight that is defined by capital M. So M is equal to summation of we have the Y of I, then that is Mi. Here summation of number of constant components. So in the container we have a two component. So there is a Y of O2 into molecular weight of O2 into Y of N2 into molecular weight of N2. So why this represents a mole fraction? There is a 0.21 into molecular weight of oxygen, that is a 32. Sorry, no, not it is a plus. There is summation which represents the plus. So plus 0.79 into, that is a 28. So after substituting the values, we are getting that the average molecular weight is equal to 28.84. This is the average molecular weight. But the molecular weight of O2 is equal to 32, then molecular weight of N2 is equal to 28, but which catch is available in the fraction of, that is 0.21 and 0.7 and 0.79 in terms of mole fractions, which has the total molecular weight of 28.84 kilogram per uh, mole. Okay, wow. Okay, so these are about the basics problems related to the concentration of fluxes and velocities and all those things. So we have a one first formula. This is related to the what gas constant, that is a PV is equal to P is equal to CRT. Please confuse, don't confuse. In some book universal constant written as R, some book it means written as R. So in both the cases you take that is called as universal gas constant. In some book it can be represented as, that is R of O2 then R of N2. For individual gases, the universal gas constant is written in terms of R. Then from that you are going to find the molar concentration. From that molar concentration you have to find the density with the help of molecular weight. After that you are having a mass fraction and mass fraction. Mass fraction related with terms of density ratios, mole fraction related with the terms of pressure ratios. Then finally you are going to find the average molecular weight. Okay, thank you.